Torque is a critical topic in physics, and every single physics exam involving rotation, you will see torque. Think back to Newton's laws. Forces cause acceleration, right? Now, torque causes angular acceleration. So just like how you apply a force to move something, you apply torque to spin something. So it's not just how much force, it also matters in what direction. Here's the standard torque equation. Torque is found by multiplying the lever arm by the amount of force. The lever arm is the perpendicular distance from the axis of rotation to the line of action from the force. Imagine from a bird's eye view, okay, this is a door. Got your two doorknobs, and it's connected with a door hinge connected to the wall. So your door can swing open this way. Imagine two scenarios. Scenario one, you push with a certain amount of force on this spot right here. The door swings open. Great. What do you think happens if you push with the exact same amount of force, but you push right here? Do you think the door is going to swing open as easily? No, it barely moves. So the force is the same, but the torque is greater because the lever arm is longer. This is why wrenches work better with long handles. Look at this longer wrench. If you push down here, it's much easier to screw this thing in compared to this smaller wrench, even if you're using the same force. Now there's a second equation for torque, and you see this quite a lot. It's if the force is being applied at an angle. So this might remind you of work and energy, but it's R F sine. This value here, R, is the distance from the pivot. What's that? Look at this circle. This, the center, would be the pivot. The pivot point. This distance here is R. Now imagine the force we're applying is at this angle. Whatever this inside angle is whatever you plug into the sine here. What's the difference between torque and force? Let's look at it. A force is a push or a pull in a straight line. Torque is kind of the same thing. But what torque is a twist or something that causes spin. Newton's second law, F equals ma, says that force causes linear acceleration. There's a rotational version of Newton's second law, which is torque causes angular acceleration. And this is actually something we'll be looking at in one of the following videos. Here's some quick rules for building your torque intuition before we solve a problem. So the first thing, more torque equals more twist. And torque is stronger with these three things. First thing, if your force is further from the pivot. Next, it's stronger when it's more perpendicular. Last, when there's a greater force. Let's look at all three of these and when they apply. So here's our door again. Let's look at the first thing that makes torque stronger. Here's the pivot, okay, the center. It's what our door rotates around. The further you are from the pivot, easier it is to rotate. That's what we looked at earlier. How about the second thing, which says that you have to be more perpendicular? If you push directly perpendicular to your door, then this would be 90 degrees. And when you look at the formula, which is this, sine 90 is equal to 1. So you get maximum torque. Now, what if your force was being pushed like this? You're pushing at the door at this weird angle. And let's say that's 45. So now it's sine 45. This is going to be less. Sine 45 is something like 0.7, which is less than 1, which means that if you push at an angle like this, you will have less torque. The last thing being bigger force equals bigger torque. This is pretty straightforward. When you push harder, there's a good chance you're going to rotate harder as well. And just like standard rotation physics and the unit circle, counterclockwise is the positive torque direction. Clockwise is the negative torque direction. If you're interested in the unit circle, I made a full masterclass for it. It's on my channel. Let's look at our first proper example problem. Let's look at human biceps. So here's your bicep. Here's your elbow and your forearm, and here's your hand. Your bicep, so this muscle here, can pull your arm up and down. It rotates around your elbow. The distance from the axis, aka your elbow, to the muscle that's being pulled up and down, which is your forearm muscle. Let's say this distance here is 4 centimeters. And let's say your bicep can pull up with 600 newtons of force. Let's analyze two situations. First one, your arm is bent at 90 degrees. The second one, your arm is bent at 45. Okay, starting with A. A is pretty straightforward. Torque is given with this formula. Lever arm multiplied by F. The lever arm, very simply, is 4 centimeters, or 0.04 meters. The force being applied is 600 newtons, which is equal to 24 newtons times meters. Torque doesn't have a specific unit of measurement. It's this, N times M. So if you ever see this, it means torque. And by the way, this is maximum torque, just like we talked about, since it's 90 degrees. So that means when your arm is bent like in this perfect L shape, that's when maximum torque is happening. What about problem B? This is a little different. How about when our arm is bent at 45 degrees like this? Say we have our shoulder and our axis, and it works something like this. Since it's 45 degrees, angles here are also 45 degrees. And of course, our R value is still 4 centimeters. That doesn't change. And the angle we choose is this one here. That's 45 degrees. The force is still 600 newtons. And the lever arm is still this many meters. The arm is at an angle below horizontal, so the effective lever arm is shorter. Let's use the angled torque formula, which is this. Torque is equal to R sine times force. Let's plug in our values. So 0.04 times sine of 45, which is 0.707 times 600 newtons. This means our torque would be smaller than it is at 90 degrees. And it is, it's 17. That's our torque. Imagine the same example. How much force do we need at 45 degrees to match the amount of torque we had at 90 degrees? Let's look at the math. So torque at 90 degrees is simply RF. Torque at 45 degrees, which is torque at an angle, is RF sine 45. This is the new big force that we need to match our torque at 90 degrees. Let's set them equal because we want the torque value to match. So RF is equal to R nu F sine 45. Rearrange for this new force value. You get force is roughly 1.14 times force. That means it's 41.4% more force required compared to when you're at 90 degrees. So for example, if at 90 degrees, to achieve a specific amount of torque, you only needed 100 newtons of force. When you're at 45 degrees, you're going to need 141 newtons of force for the same amount of rotation. Here's something to finish up this video. When more than one torque is acting on your object, angular acceleration is proportional to the net torque. So if your torque is going in the same direction, then the net torque would be all of the torques added up, so the sum. If the torques are moving in different direction, then the net torque would be the difference between them because they're opposing each other. And for what's torque is positive and negative, follow the unit circle angles. Again, the unit circle is super important in physics. Go check out the video I made on it. In the next video, I'll be talking about the dynamics of torque and solving torque problems with inertia. This is a crucial topic, so I recommend you go check it out. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.